Okay, physics time. Here we go. We're doing, let me put that away. My cord is hanging out. Give me a second. I'm going to tuck it into my belt. No. It isn't. It isn't. It's the microphone cord. I won't repeat that question for the mic. Anyhow, we're talking about physics, and we're specifically talking about, let's name this one energy calculations. Energy calculations. We've done a couple. We did the one for work, which you need to remember. Of course, we did the one for power, which you need to remember. Your book has equations for efficiency and mechanical advantage of simple machines, which you should read about and know about them. You don't need to have the equations memorized. And now we're going to talk about the equations for kinetic and potential energy. So let's just write them down. K equals 1/2 mv squared, where K, guess, kinetic energy. Good. We'll talk about how. But what is kinetic energy going to be measured in? As energy is always measured in joules. Joules. Not always, but in the SI we measure energy in joules. Does anyone know what I wouldn't even call it in English, but an alternative unit for energy measure? What might that be? Do you remember? Physical science? No, that's a measure of power. How do you measure food energy? Calories. Yeah. Any kind of energy, but we generally, for dietary reasons, use calories. And although in the European Union, in almost every you will find the energy readings on the back of like a bag of Twinkies. Europe's weird. But they'll be joules too, just like kinetic energy is measured in joules. Anyway, K is kinetic energy measured in joules. 1/2 is just 1/2. That's a unitless thing. It's just 1/2. M is mass measured in kilograms, and V, lowercase v, arrow, meters per second. But that's not it, is it? Numerically, we also square meters and we square seconds. So our unit ends up being kilogram per meter squared times meter squared per second squared, which again is equal to a joule. Just like work was a force, kilogram meter per second squared, times the distance in meters, which came out to be kilogram meter squared per second squared. So look, this is two ways to skin. The unit is joules for both work, which we calculated by FD, and kinetic energy, which we calculated by 1/2 mv squared. The unit still comes out to be joules, and the mass still turns out to be kilogram meter squared per second squared. What about potential energy? U. This is specifically gravitational potential energy, equals mgh. U is, as I just said, gravitational potential energy. Where are we probably going to measure gravitational potential energy in? Joules. Joule is energy. Where M is mass measured in kilograms. G is the universal gravitational constant is capital G. This is lowercase g. It's the gravitational acceleration, or what you might say, acceleration due to gravity. And for this, we don't only have a unit, but on Earth, we also have a value. What is it? 9.8 meters per second squared on Earth surface. And then h is height, measured in meters. Now this time, we have kilogram times meter per second squared times meter. What's that unit all together? Those are going to add up to or multiply to kilogram meter squared per second squared, which is again a joule. Ways to skin a cat. Do you know what I mean by that? That's a metaphor. Obviously, we're not literally skinning cats. What do I mean by 3 ways to skin a cat? Well, we have the exact same. So yeah, we're in each of these cases, the one that I'm saying for the third is the one we already did in the last video called W equals FD. And all of these, whoa! Energy is measured in joules, which is equal to kilogram meter squared per second squared. But the way we got to it is a completely different set of variables. What does that tell us about energy? That tells us something great and excellent, and the main point of science tells us about energy what? Yeah, all energy is what? It's yes, I like that, but that's not what I'm looking for. Conserved. Energy can be transferred, conserved, and I'm going to put that transferable. Energy can be transferred, it can be transformed, but it's always conserved. Okay, so here's the classic example. If I have my mystery object up there, do you see it? Don't talk about it. The camera has never seen this, and it's never going to. Yeah, do you see my mystery object up there? If the mystery object, let's say the mystery object has a weight of 362, mass, 362 kilograms. The mystery object, it could have any mass, but I'm going to say it has a mass of 362 kilograms. And it's about 62 meters up in the air, isn't it? You can't see it. The camera can't see it. It has no idea. Don't talk about it. It's 62, it is that high. And it's on Earth's surface. So G equals 9.8 meters per second squared. How much potential energy does it have? Well, let's calculate it. U equals mgh. This is a very simple calculation. U equals 362 kilograms times 9.8 meters per second squared times the height is 62 meters. U equals, math that up please, boys. Time for math lab. Time to do some methamphetamine. Nope, 362, which is its real true mass. That's the amount of matter the object that cannot be named has. 219,000, we'll just call that good. 219,000 joules.
So what did you do? Let's do 220, because it's 900.
Okay. Jacob freaking Reich messed my erasers up by putting them in a straight line. I cannot stand that. 220,000 joules.
So what did you do to get 200?
We multiplied the mass by the acceleration due to gravity by the height. But that's not the point. I mean, that's part of the point. How much potential energy does the unnamed, unknowable, unreckonable object have? Well, that's how much potential energy it has. But what I'm getting at here, falls, which it would never do because of the laws of physics. This is an object that is immovable, unknowable, unthinkable, unconscionable. But if it were to fall, hypothetically, for the sake of our energy equation, yeah. I'm not going to draw it either because just drawing it will attract the ire of the eldritch gods. As it falls, let's say it's halfway down its 62-meter flight path. What is true about its energy right here?
It's the same.
Yeah, so what equals what here?
Kinetic energy equals potential energy.
Yeah, at this point, K equals U. Is that true the entire way? No. Entire way, at any given point of its path, K plus U equals what we call the quantity, potential energy plus kinetic energy. Do you remember? Mechanical energy. And this amount doesn't change if what is true? Even if it's not true, no, it's always true, even if this isn't true. But if we negate what, is this true? If we negate friction. In reality, which this thing is not part of reality, but if it were, and in reality, if it were falling, some of the energy would be lost as friction. Okay? So then right before it lands, ground, in the millisecond when it's barely touching the ground, but it's still technically falling, what is true of its energy? Does it have potential energy? What's its height?
No potential energy.
Right. Has no height. What must also be true? It has entirely kinetic. It's all kinetic energy. So what else must be true of its velocity?
Its velocity is 0.
No? Its height is 0, so its velocity must be, not necessarily a number, but its height must be its velocity must be the highest of any point here. As it falls, it gets lower and lower, but also faster and faster. And that's due to the law of conservation of energy. Now, if we don't negate friction and deformation and sound, as it falls, it loses a little bit of that energy as friction. And then when it actually falls, all of the energy that is lost in the environment in the form of friction, which is heat, deformation, which means it breaks or changes shape, that really what's happening there is some of the energy is going to breaking or forming new chemical bonds. And then sound. Sound is energy that is considered waste energy also. Anytime there's a collision, those three things the energy is lost. It's not really lost, but the energy is transferred to the environment through those three methods. So when I throw the marker, it stops because what? Does it still have kinetic and potential energy? It has no kinetic or potential energy right now. Where did all the energy go? It vanished? That can't be true because of this. So where's all the energy now that was in that marker? Thermal energy? So the environment around where it was is a microscopic amount warmer, but true. It's a tiny amount, but it's a true amount warmer. There was some deformation, and the marker deformed. You heard the sound, and all that was contained in its flight is now in those three places. It's spread out into the environment. So what does this imply about the universe? If we look at the long scale, what gonna?
It's all gonna.
All of it, all the energy at some point, be heat. Everything will be heat. Other kind of energy. The heat death of the universe. Bye.